This is stuff that's kind of going to be a little bit of review, but the basics of calorimetry are that the changes in potential energy of a reaction are then reflected in the change of the kinetic energy of the water. This is why we have a temperature change of the water in a calorimeter. So we're going to break this down to exothermic and endothermic reactions and talk a little bit more what that means about stability. So in an exothermic reaction, we have potential energy that is lost from the reaction, which is then converted into kinetic energy that is gained by the water. So if we're gaining energy in the water, the temp of the water increases because of the faster movement of the molecules. Should say molecules there. This is true. So when we think about this, I love visual aids. And so we're going to think about this like a graph. And so I'm going to write out our typical reaction equation, just generic. We have some sort of reactants that then go to products. Where's energy in an exothermic reaction? Exactly. So plus energy. Now, if we think about the form of energy, each of these things are both of our reactants and products we measure in potential energy. Because remember, in chemistry, it's the bonds and the intermolecular forces that we talk about. What is the energy that we produce? What does that get converted to? Kinetic. So how we graphically show this transition, I'm going to just do it generically. I'm going to pick just two different levels of potential energy. What starts off at the higher potential energy? The reactants. We have some amount. Then what happens is we release energy and we have a lower potential energy products. So this section is released energy, which then this is what turns into our kinetic energy. What sign for exothermic for delta H? Exactly. So this is negative delta H. So if it helps to think about this graphically, it's a negative slope. We're negatively losing this energy into our surroundings, into the water. Any questions about this? Now, in an endothermic reaction, we have kinetic energy that is lost from the water and becomes converted into potential energy gained by the reaction. So if we're losing kinetic energy in water, exactly, the temperature decreases. All right, so if we think about the generic reaction for this, we have reactants. These are gaining energy in order to turn into their products. And the types of energy associated with these are just the same, where we have our reactants and our products that are some form of potential, and our energy term will be kinetic. And then if we look at this graph here, I'm going to do a same, oops, different color though, axes titles with potential energy and just a scale of time. And so this is supposed to just represent as time goes on. I forgot to mention that for the first one. But so here, do you think our reactants will start at a lower or upper line? Lower, yes, it's opposite. Then they rise in energy because they took that away from the water. I wrote P instead of R there, guys. There we go. Call me out. Big story. All right. This now is energy absorbed by water. Or from water, not by water. So this is positive delta H. Any questions about kind of recapping this transfer? Is it kind of starting to sink in a little bit now we've heard it a few times? I know yesterday it was kind of like clunky, but is it starting to make more sense, the transfer and conversion, where it comes from? Okay, awesome. Okay, so in terms of stability, we talked about a couple things, or this was on your problem set yesterday. And so for those of you that I talked to, this is like kind of what I was trying to explain, is that exothermic products have lower potential energy. Endothermic products have higher. So if we first break down exothermic, and compare, well, actually, let's just compare them each other right away. If you have more potential locked and loaded in your bonds, do you think you're stable or unstable? Unstable. You have more potential to react with something else. So that's a way to think about it. So that means exothermic products that have lower energy at the end, those are going to be stable. Then endothermic will be unstable. Any questions about that concept? Coolio. So the reason why we can use calorimetry is because we know the rate of which water converts potential energy into kinetic. And so we already talked about this term quite a bit. This is literally specific heat. So because we know specific heat is why we can use calorimetry. But I just want to point out that this number is only for the liquid state. And so there's going to be different constants that we'll use, especially when we start talking about heat of fusion and vaporization, which these are just at the points that water freezes or turns into a gas. So we'll have some different calculations we'll use during phase change diagrams in a later section. But I just want to start this idea that this value is only for when water is liquid. And so we're going to finish up your pre-lab today because we're going to talk all about the mathematical relationship we can use to determine all sorts of stuff that has to do with heat. And so the formula here is Q equals MC delta T. So I will call this Q MCAT. But for Q, so Q is the quantity of heat. So when we talk about the unit of joules, so Q is the heat that we determine. M is mass. So you guys have seen that variable before. We use grams. And the reason why we use joules and grams has to do with the specific heat. Units being joules over grams times degrees Celsius, which means our temperature change has to be in degrees Celsius as well. So one thing I want to write here is what does delta T represent? So what minus what? You guys know what it means to be delta? Yes. So, but how I'm going to teach you guys is, or define it, T final. So the final temperature minus the initial, T initial. So you may also see me write this as TF minus TI. So technically delta T represents two terms inside itself. So one thing, you'll never have to really worry about C. C will always be 4.18. So it's really the Q, M, and the two T terms that we're going to be playing around with. So let's do some math. But before we do that, I want to talk about a fancier calorimeter. So ours were pretty ratchet. I'm not going to lie. A lot of them leaked. You guys will probably find from your post lab that the numbers you get are not very close to the accepted. But this has to do with, think about how many directions could you have lost the heat input? A lot. It's not a closed off system. So I want to show you, this is actually called the bomb calorimeter because you explode stuff inside it. So I remember the first time in my physical chemistry class, they're like, oh, we're working with a bomb calorimeter. We're going to create a bomb today. It was so exciting. All you stare at is like a silver container. You don't hear anything, you don't feel anything, and it just collects data. So they're actually not as cool as they sound, but how they function is neat because you have to obviously have everything sealed off to get the most accurate measurements. Yeah, so it's pretty much what ends up happening is you have a vessel. So like this inner vessel, this is where you have whatever your reaction is, and they usually hook it up to something that will ignite it. So you place that in there, you seal that off. You have a thermometer that's pretty tightly sealed, and then that is put into a mass of water that you know. Same idea. Like I said, it's just a lot more accurate of results. So I just wanted to show you what an actual one kind of looks like. Any questions about how it functions? Okay. All right, let's do some calculations. So starting with the first one, we're gonna practice calculating the number of joules absorbed. You guys remember what letter represents this in the equation? It is Q. So we're, oops, I need my pen. Q. So I'm gonna write up here, this is what we're gonna work with for the rest. Oops, that's not a. All right. I'm gonna, okay, so typically how I do my math problems is I write out what all my quantities are. So Q, that's what we're solving for. So I usually do a question mark. Reading this problem, how many joules are absorbed by 100 grams of water? What's our mass? 100 grams. All right. What is C? 4.18. Anyone remember the units? Look at you guys go. All right. And the last thing we need is delta T. So what is our final minus initial temp? 50 is the final. Minus 35. So I took the final temperature because it was increased from 35 to 50. I took the final minus the initial of 35 to get our delta T, or our change in temperature of 15 degrees C. And so all that's left to do here is plug it all in. So we have Q is equal to 100 grams times 4.18 joules per grams degrees Celsius times 15 degrees C. Okay, so if we solve for M, I'm going to give this little circle. We are going to divide both sides by C delta T as a nice little algebra reminder. And then we are going to get that M is equal to Q over C delta T. So we have our equation rearranged. Determining our terms now. So Q, that's our heat. So what has joules associated to it? What number in there? 80. So our Q is 80.0 joules. C will always be our 4.18 as long as we are working with liquid water. And then our delta T. So this problem, it tells us that the water's heated by 20 degrees C. Do we need to do any calculations for delta T? No. This one's kind of nice. It's very nice, yes. Okay, so now the last thing we do is plug it in. M is equal to 80 joules divided by 4.18 times 20. Oops, and I put the parentheses too soon. The answer is, I'm going to actually write it down, 0.957 grams. Any questions about either of those that we just did? Bless you. You should have, oh, after I cleaned out that back room and, you know, breathed in 40-year-old dust. So now we're calculating the temperature change. So we're looking for delta T. Start with our Q equals MC delta T. And the nice thing about having a very linear equation, you just pretty much have to throw the other variables to the other side. So delta T is equal to Q over MC. What's Q in this case? Beautiful. 300 joules. What's our mass of water? 50. and C is our 4.18. You guys are going to get sick of specific heat. No, it's 50 dot. That's just how I define sig figs as 2 sig figs. Any other questions? Okay. All right, delta T is equal to 300 divided by 50 times 4.18 J over grams times delta C. You get that it's 1.4 degrees Celsius. And now here's the question. Is the water getting warmer or colder?
If energy is absorbed by it, then it's
warmer.
Good job, guys. Okay. All right. Last one here. Now we are still, so we're looking for the initial or final. Doesn't matter which one you're looking for. You still have to solve for delta T, but then you're breaking it down into delta T's T final minus T initial to get this. So we already know that delta T is equal to Q over MC. So again, we have to go through and define what each of those are. Q is 200. M is 80. And then our delta T, oh, never mind. That's not what I meant to do. C is 4.18. So we are going to solve for our delta T with our 200 joules over our 80 grams of water times our specific heat of 4.18. If we calculate that out, we get a temperature change of 0.598. Are we done? No. No. So what is the question asking for? What temperature? Exactly. So if we were to rearrange, T final is equal to delta T plus TI. So then we have our change of 0.598 plus, what's our initial? $25.000. What's our final answer then? You got it. When you're adding, sig figs is decimals. They have the same amount of decimals, so you don't have to drop any. All right, any questions?